In this video, I'm going to give you guys a review over carrier-mediated transport. So to begin with, this table shows you carrier-mediated transport, also known as facilitated transport. This is a two-part table. What you want to do is make sure that you can understand the description of each transport process as seen in the second column. Make sure you can classify each as passive or active, understanding why it is such, and understand what's going to be transported in this fashion. To begin with, we start with facilitated diffusion. Recall that diffusion of particles is going to be movement from a high to a low concentration gradient, and this is done through a selectively permeable membrane, such as the plasma membrane. Because what's being transported is considered large, charged, or polar solutes, these cannot pass directly through a membrane. For that reason, you must have a channel or a carrier protein to facilitate that movement across the membrane. Now, because it's diffusion, it's considered a passive process. The chemicals that we're looking at are moving down a concentration gradient. So in this example, I show you a concentration of sodium ions that are higher in the ECF and a lower concentration of sodium ions in the ICF. Because these are charged particles, they cannot pass directly through the plasma membrane, so you'll see that there is a channel or a carrier right there to allow their transport. Now, since we know diffusion is going to take place, sodium itself is going to move from a high to a low concentration gradient into the ICF. Now, this is considered uniport, or this channel is considered a uniport, and that's because it's only transporting one entity. Now, this again is an example of facilitated diffusion because sodium is still diffusing down its concentration gradient, but the use of the channel makes it facilitated or carrier mediated. And finally, it's passive transport. No ATP is required because the sodium is moving down its concentration gradient. This is a great example of how to sit and look at the scenario and actually answer questions on your own. And so this shows you another example of this facilitated diffusion. Right here, where the particles are in a higher concentration in the ECF than in the ICF, so they travel down their concentration gradient into the ICF using a carrier protein. So you can follow the steps here. Read these questions and take a minute to answer them. Pause the video and answer it on your own, and then when you press play, I'll give you the answer. So the question first off asks, why would this solute require a carrier? Well, this solute would require a carrier because it is unable to pass directly through the plasma membrane. Recall that anything that can pass through uses simple diffusion, and it has to be small, non-charged, and non-polar. That means that anything that's using this carrier is likely a large molecule that cannot pass directly through the membrane unassisted, or it's charged like a sodium ion, or it is polar. The second is, why is this considered a passive process? Because diffusion is taking place, you have the solute itself moving down a concentration gradient from high to low concentration. This does not require ATP, so it is considered passive. As you move to the next example, you're looking at primary active transport. By definition, it's the transport of solute particles through a selectively permeable membrane. The difference here is that now they're moving against their concentration gradient. They'll use a carrier protein known as an antiport, and this is going to be considered active. Again, this is active, meaning it requires ATP. As it says in the definition, this is solute that's moving against their concentration gradient. Keep in mind that once again, we are looking at movement that requires a channel or a carrier protein. And so here, you can see it compared with our facilitated diffusion example, and here is going to be our primary active transport. Now, as you can see, you still have a higher concentration of sodium in the ECF compared to the ICF. But as you look at potassium, you see that potassium has a higher concentration in the ICF than in the ECF. Now, if we were talking about diffusion, you would see sodium moving down its concentration gradient into the cell. Likewise, if we were talking about diffusion of potassium, potassium would move down its concentration gradient out of the cell. However, we are looking at a mechanism by which you now push these ions against their concentration gradient. What that means is that using ATP to power this movement, you're now going to push sodium from an area of low concentration to high concentration against its concentration gradient. Likewise, you're going to push potassium from a low concentration to a high concentration. The reason this requires a protein of some kind is twofold. First off, again, you're moving charged particles, so they can't cross directly through the plasma membrane. But even if these were small, uncharged, and nonpolar, you would still need a protein in order to actually push them against their concentration gradients. So again, watching that movement of those ions, you're reminded that this is primary active transport. That channel itself relies directly on hydrolysis of ATP. This is an example of countertransport because you have two solutes moving in opposite directions, counter to one another. In this example, this shows you step by step what's happening in this primary active transport. This is the sodium-potassium pump. It's a great example of primary active transport. What I want you to do is either watch the video or read in your textbook or just study the picture that you see here. And I want you to write out step by step how a sodium-potassium pump would work. Then I want you to consider why it's primary active transport and tell me if it's considered co-transport or counter-transport. So pause the video, work through it on your own, and then when you come back, I'll give you the answers. In this mechanism, the sodium-potassium pump works, once again, by pushing sodium and potassium against their concentration gradients. Here you would see that with a low concentration of sodium inside the cell, sodium can be pushed against that gradient by entering the sodium-potassium pump, with 3 sodium ions binding at one time and then being transferred to the extracellular fluid, where they are already in a higher concentration. In an opposite direction, which is why this is considered countertransport, potassium ions, which you see in the ECF, are going to enter this carrier protein, and they're going to bind in 2 active sites. And so 2 of those potassium ions will be pushed against their concentration gradient into the intracellular fluid. This is again considered primary active transport for 2 reasons. It's active, meaning it requires ATP, because both ions are being pushed against their concentration gradient. It's considered primary active because this protein pump itself is harvesting ATP. The next mechanism we look at is secondary active transport. This is going to be the transport of solute particles through their selectively permeable membrane against their concentration gradient. Again, it's going to require a channel or a carrier, but the difference is that this one does not directly consume ATP. So it is going to be active, and this is what's tricky, is that even though it doesn't directly consume ATP, you're still using movement of some kind of a solute against its concentration gradient. Now, what this means is that it's going to rely on a concentration gradient that's established elsewhere in the membrane. This component, right, the concentration gradients established elsewhere in the membrane, this is usually a form of primary active transport. And so even though the secondary active transport doesn't directly harvest ATP, usually the concentration gradient that's established elsewhere did require ATP. Again, in most cases here, we're looking at solutes that are being moved against their concentration gradients, but it's not always the case. So we've looked at countertransport with your primary active transport and the sodium-potassium pump. This is going to be a great example of co-transport, where you have solutes moving in the same direction, and we refer to this kind of a carrier protein as a symport. And so here you can see our facilitated diffusion from the first example. Here's our primary active transport of the sodium-potassium pump, and in this last example, you see your sodium-glucose transporter. Now, in this particular example, we're showing that glucose is a higher concentration in the ECF, as does sodium. When you're looking at cells within the kidney, frequently the glucose concentration is flipped, with a higher concentration of glucose in the ICF and a lower in the ECF. So you may see differences between videos that you see on YouTube and what you see in the textbook. I've gone ahead and chosen the easier mechanism here, where you actually have glucose and sodium moving down their concentration gradients. So the reason you would actually need ATP to be used at all is as follows. In order for sodium and glucose to move from the ECF into the ICF, they both bind simultaneously to this channel. So I'll show you that again. They move simultaneously through the channel into the ICF. This means that in order for glucose to enter these cells and be stored, sodium needs to be able to continue to enter the cell. Well, keep in mind, anytime an ion or any solute is moving down their concentration gradient, just as sodium is doing now, they'll stop movement whenever they reach chemical equilibrium. Well, there's a great potential for that to occur if sodium continues to flow through this channel and build up its concentration here in the ECF. The problem is that if sodium reaches chemical equilibrium, then glucose can no longer travel with it into the cell, and glucose import stops. Well, along that cell, you should also have a sodium-potassium pump running at all times. And as you'll recall, the job of a sodium-potassium pump is to remove sodium ions from the ICF, depositing them back into the ECF. And so these sodium ions that are coming into the cell using the sodium glucose transporter can essentially be pushed back out of the cell using the sodium-potassium pump. This prevents sodium from reaching equilibrium, meaning sodium and glucose alike can continue to move into the cell, allowing glucose to be stored. Now again, this is considered secondary active transport because that transport protein does not itself directly harvest ATP, but it relies on a concentration gradient that is established elsewhere, such as with the sodium-potassium pump. Again, this is an example of co-transport because you're moving these ions and solutes in the same direction. So here you have a schematic of your sodium glucose transporter. And this is showing you the mechanism of action. And you want to answer the questions here while I've got the video paused. So pause your video and answer the questions the best you can. And then once you've done that, come back and listen to the explanation. So the mechanism of action here of the sodium glucose transporter can be seen in this spot. Here you can see co-transport of glucose and sodium through the SGLT into the cell. Now with sodium moving down its concentration gradient, it needs to never reach chemical equilibrium to allow this process to continue. And so running simultaneous to the sodium glucose transporter, you have a sodium-potassium pump, which using ATP is removing sodium from the ICF to the ECF all the time. As long as the sodium-potassium pump continues to run, you'll continue to have a concentration gradient of sodium, allowing it to enter the cell, thus bringing glucose along with it for storage. It's considered secondary active transport because the sodium glucose transporter does not itself use ATP, but it does rely on a concentration gradient that's established elsewhere in the membrane. Here, the sodium-potassium pump is at establishment. This SGLT is using a protein that is known as a symport protein because it is using co-transport with both glucose and sodium moving in the same direction. That's the end of that video. Please make sure that you go back to any section that you need to clarify terminology. Keep in mind that I'll give you examples of transport and ask you to use any of the terminology we've looked at so far.